So first of all, thank you very much for everyone who are attending today's lecture. So this is a lecture number 6 from our course TR3011 Aerodynamics 2 Compressible Aerodynamics. Okay, so this is basically the third topic for our compressible aerodynamics subject. The third topic is called oblique shock and expansion wave. So what we have done so far for the past 5 weeks, we have already looked at the introduction to compressible flow, and then on the second topic, we look into the normal shock. So this is the continuation. So we will look now on the oblique shock and expansion wave. In terms of the subtopic for this particular topic on oblique shock and expansion wave, so these are the subtopic that we are going to cover. So we will look into the overview. We will then touch upon the oblique shock relations, and then we will continue on supersonic flow over wedges and cones. And the fourth subtopic is shock interactions and reflections. And then the fifth one is detached shock wave in front of a blunt body. And we will look into the last topic, which is Prandtl-Meyer expansion wave, before we summarize this particular topic on oblique shock and expansion wave. So for today, we will look at the first two subtopic, which is the overview and the oblique shock relations. All right. So basically, in our previous lecture on normal shock, we have already discussed on the what we call it as the normal shock waves. That is a shock wave that make an angle of 90 degree with the upstream flow. So this is basically the condition that we normally look at for normal shock wave. And if you can recap back what's going on the point 1, going through the thin layer of normal shock wave and goes into condition of point number 2. So there are variations in terms of the Mach number, the velocity, the pressure, density, temperature, entropy, P01 and enthalpy 01. Okay, and a shock wave that make an oblique angle. So this is when it is a normal shock wave, it is at angle 90 degree. But what happened when the shock wave make an oblique angle? So with respect to the upstream flow, so similarly here, it is no longer 90 degree, it is at angle of theta. So it is normally called as oblique shock waves, right? So for example, like what being shown in these two photos, the first, this is a shuttle and this is just a cone shape at an angle. So, and a normal shock wave is simply a special case for the general family of oblique shock, namely the case where the wave angle is 90 degree, we call it as a normal shock wave. Anything having different angles, okay, other than 90 degree, it is oblique shock wave, right? Similarly with that, so there will be a variation of the properties of the flow at point 1, and then there will be properties at point number 2 that we are going to investigate in this particular topic. So in addition to the oblique shock waves, where the static pressure increases, right? So in the oblique shock wave, static pressure increases across the wave, but there are also a supersonic flows, also known by oblique expansion wave, right? So there will be oblique shock and oblique expansion wave. There are two conditions over there. Condition number 1, concave corner, and condition number 2, convex corner, right? So you can see here the position of the theta where the flow being deflected are different between the concave corner, right? And you have a positive theta there. For convex corner, it is you have a negative value of theta, where you will experience expansion fan, right? Where in this particular case, for the oblique expansion wave, the static pressure decreases across the wave. Whereas for the oblique shock, for concave corner, you will have the static pressure to be increases. So that's the two fundamental differences between the oblique shock and the expansion fan. So let us examine these two type of wave. So as we can see here, for the first case, the flow field properties are a function of the X and Y direction. It is in 2D, in contrast to the one-dimensional X direction for normal shock wave, because the flow is being deflected. Okay, and the flow for the convex corner, and the flow at the wall must be tangent to the wall, hence the streamline at the wall is also deflected outward and downward through the angle theta. Okay, so I hope you can already see the basic differences between the two conditions. So what is actually the physical source? The physical source of the oblique wave. So the physical mechanism that creates waves in a supersonic flow, right? If we look here for the subsonic flow, imagine there is a flow moving slower than the speed of sound because it is a subsonic flow. The Mach number free stream, which is less than 1, right? Where we can see here the disturbance due to body is propagated upstream via molecular collisions at approximately the speed of sound. So the gas molecules which impact the body surface. So imagine the gas, the air molecule impacted the surface of the body, experience a change in momentum. All right. So in turn, this change is transmitted to neighboring molecules because it's being deflected, okay, because subjected to the collisions, and is transmitted to neighboring molecules by random molecular collisions, okay. So when we look at for supersonic flow, right? So again, now the free stream Mach number is more than 1. The flow moving faster than the speed of sound, okay, and there will be a shock wave being developed, where disturbance due to body is propagated upstream via molecular collisions at approximately the speed of sound, where disturbances cannot work their way upstream because of this shock wave formation. So in this fashion, information about the presence of the body attempts to be transmitted to the surrounding flow via molecular collisions, and that is the information is propagated upstream at approximately the local speed of sound, right? So this is just the how to visualize what's going on. We will look into much further over here. So if we look here for subsonic flow, if the upstream flow is subsonic, okay, if the upstream flow is subsonic, which is less than 1, as shown in this particular figure, the disturbances have no problem working their way far upstream. So basically, when the molecules of air are being bounced back, okay, and basically thus giving the incoming flow plenty of time to move out the way of the body. Basically, when it is reaching the body of the surface, it can now be deflected around the body instead of hitting the body. This is in the case of the subsonic flow. However, for the supersonic flow, so this is imagine this is the incoming, the green balls are the incoming air molecules, the blue balls are the deflected one. So if the upstream flow is supersonic, as shown over here, the disturbances cannot work their way upstream, rather at some finite distance from the body, and the disturbance waves pile up and coalesce, forming a standing wave in front of the body. Hence, the physical generation of waves in a supersonic flow are both shock waves and expansion waves. All right, so that's the physical meaning. So why are most waves oblique rather than normal to the upstream flow? So in actual cases, you will be seeing more oblique shock rather than the normal shock. Okay, so consider a beeper moving through the gas in a subsonic and supersonic condition. So this is a beeper moving in a subsonic condition, and this one is moving in a supersonic condition as shown in figure A and B, where for subsonic, the velocity of the moving beeper is less than the speed of sound, whereas in supersonic, the velocity is more than speed of sound. So first, what we need to do is basically to consider the beeper moving at subsonic speed through the gas as shown in the figure A just now. So the speed of the beeper is V. We name it as V, where V is considered to be less than A, which is the speed of sound. At time t equal to 0, the beeper is located at point A. So this is the initial point at time t equal to 0. Right? So at this point, it emits a sound wave that propagates in all directions. So it is not just in one direction, it is basically in many directions at the speed of sound A. All right. So during its transit from point A to point B, the beeper has emitted several other sound waves because it is not just one sound wave, which at time t are represented by smaller circles. So at time 1 point, and then another wave being generated and another wave being generated. Okay, so note that the beeper always stay inside the family of the circular sound wave, and the wave continuously move ahead of the beeper. All right. Okay, now consider the other condition. At supersonic speed through the gas as shown here, the beeper moving at a supersonic speed more than the speed of sound as shown here. Right? At time t, at point A, where it emits a sound wave, during its transit from A to B, the beeper has emitted again the same thing, several other sound waves, which at time t are represented by a smaller circles. Okay, the beeper is now constantly outside the family of circular sound. That is, it is moving ahead of the wavefront because of the nature, because the velocity is more than the speed of sound. So it is much faster. All right, so that's the two differences between subsonic speed and supersonic speed, where velocity is either less than the speed of sound or the velocity is greater than the speed of sound. Moreover, something new is happening here. These wavefronts form a disturbance envelope and given by the straight line BC. So imagine A going to B, right? So, and this is the straight line BC, which is tangent to the family of the circles. And this line of disturbances is defined as the Mach wave. So this line, this tangent line is called the Mach wave. Simple or initial sound wave. So the angle AB to C, this is the angle, okay, mu, which is called the Mach angle, which is basically the Mach wave makes with respect to the direction of motion of the beeper is defined as the Mach angle mu. From the geometry in this figure, so we readily find that sine of the mu equal to the speed of sound times the time taken divided by the velocity times the time taken, which is then equal to A over V, which is also equal to 1 over the Mach number. So the Mach angle, the Mach angle mu is basically the sine to the power -1 of 1 over Mach number. All right. Right. By referring to the figure, this particular figure, if the disturbances are stronger than a simple sound wave, right, then the wave front becomes stronger than a Mach wave, right, creating an oblique shock wave at an angle beta, instead of just having Mach wave, Mach angle. We now have a because the Mach wave is getting stronger, so we have oblique shock wave at an angle beta to the free stream, where beta is greater than the mu. Beta is greater than the Mach angle. However, the physical mechanism creating the oblique shock is essentially the same as what being described for the Mach wave. Indeed, a Mach wave is a limiting case for oblique shock. So it is an infinitely weak oblique shock or initial of shock wave. So basically, the Mach angle is the minimum oblique shock angle. So this is the least it can be. It is called the infinitely weak oblique shock, and what we have created here basically a much greater angle for the oblique shock. Right. So this basically finishes our discussion for the physical source of the oblique waves in a supersonic flow. As usual, I'm showing the plan for this particular topic. Before we proceed further, let us now look to develop the equation that allows us to calculate the change in properties. Like normal shock, we need to relook at the properties changes. But first for oblique shock wave and then for expansion wave. So the process of the roadmap is given over here, where now we already look at the source of oblique wave. We will look at the this part of first, oblique shock relations, supersonic flow, overwidth and cones, and then shock interaction and reflection and detect shock wave. And then at the same time, we are going to look at Prandtl-Meyer expansion wave before we conclude into shock expansion theory, application to supersonic airfoil. Before we go into the next subtopic, right? Let us look into an example given in the Anderson book, example 3.1. Basically, if you look at the book, it is example 9.1. So imagine a supersonic airplane, right? As shown in this particular figure, traveling at Mach 2 at an altitude of 16 kilometers. So assume the shock wave pattern from the airplane in this figure quickly coalesces into a Mach wave that intersects the ground behind the airplane, causing a sonic boom. So this is no longer at 90 degrees to the free stream. It is at an angle where a sonic boom which is heard by a bystander on the ground. So at the instant of the sonic boom is heard, so you have to calculate how far ahead of the bystander is the airplane. All right. So basically, what we need to find is D. So we want to find D over here, where in this particular figure, where you have the vehicle over there, the aircraft, right? And this is just a schematic of what is mu, the Mach angle. This is the altitude that it is flying at 16 kilometers at Mach 2. So this is where the bystander, the man or the woman standing. We need to find the D. So by examining this particular figure, we show the airplane at an altitude of 16 kilometers with a Mach wave trailing behind it, and the Mach wave intersect the ground at a ground distance of D. So this is the distance of D from the equation that we have already shown earlier. So Mach angle equal to the sine to power minus 1 times the 1 over the Mach number. All right, you will get the Mach angle to become 30 degrees. So basically, this mu is 30 degree and this is 30 degree. And from that figure, you find the tangent, a tangent u mu, which is equal 16 kilometer over D, and you solve it, you will get the D to become 27.7 kilometer, right? That's how fast the aircraft travel at Mach 2, and the distance basically 27.7 kilometer from the aircraft. All right. Okay, so that is basically just an introduction and the overview of the oblique shock and expansion wave. So now we want to move into the oblique shock relations. Okay, with regards to this, this is what we want to show the oblique shock geometry. So we have we want to consider the oblique shock wave sketched in this particular figure, right? So the angle between the shock wave and the upstream flow is defined as the wave angle, right? So basically, this is the direction of the flow, and this is the oblique shock, right? Oblique shock shock wave basically, and then that angle with respect to the flow direction is what we call as the wave angle beta. All right, so let us examine this particular figure in more detail. And sides A and D, so we have the side A and side D over here, all right? So parallel to the shock wave. So because this is being enlarged, if you can see over here, so we are taking now considering this particular position. So we just want to enlarge it. So we take that as the artificial dotted line over there, side A and side B. Whereas segment B and C follow the upper streamline, and segment E and F follow the lower streamline. All right. So I hope it is large enough for all of you to see what's going on. All right. And then let us apply the integral form of the continuity equations to this oblique control volume. Similarly with our normal shock wave, so we are going to consider the continuity equation. Important facts for flow is steady, and the flow is steady, right? This is the condition, and the flow is also adiabatic. Q dot no heat transfer, and Q dot equal to 0. Is no viscous effect, the mu equal to 0, no body force, F equal to 0, 2D flow where V equal to U and W in the direction of X and Y. All right. So looking at the continuity equations, where when we have steady flow condition, the change in the time equal to 0, right? So we use the same previous normal shock wave technique solution. So where this surface integral evaluated over faces A and D, which yields, remember, A and D, this side and this particular side, right? So which yields to have this expression of the minus density 1 U1 times A1 plus density 2 U2 times A2, and where W direction will be 0, which is parallel to faces A and B, right? And A1 will equal to A2, and while faces B, C, E, and F are parallel to the velocity and hence contribute nothing to the surface integral, right? So thus the continuity equation for oblique shock wave can be expressed as this, right? So in terms of rho UA at 1 and plus rho UA at 2, and then we rearrange that, so we get rho 1 U1 equal to rho 2 U2, where U1 and U2 in the equation are normal to the shock wave. All right, let us now apply the integral form of the momentum equations to the oblique control volume. So we have the expression for the momentum equation, where we know that it is a steady flow condition. Again, use the same previous normal shock wave technique solution, where we know momentum is a vector equation. Hence, we can resolve into two components. One is tangential to the shock wave, and the other one is normal component to the shock wave. So you have the tangential component, and then you have also the normal component. So looking over here, right, for the tangential component, where W is the component of the velocity tangential to the wave. So you have maybe you are asking, where is W? This is W2, right? So W2, okay. And since the ds is perpendicular to the control surface, right, then the PDS, the change in pressure with respect to the entropy tangential over faces A and for faces D is 0. Also, since the vector PDS, okay, on faces B and E, okay, are equal and opposite, the pressure integral in equation involve two tangential forces that cancel each other over faces B and E. And the same is true for faces C and F as well. So it becomes, so you can rewrite that, okay, and divided it by the earlier expression from continuity, right? So we have W1 equal to W2, right? Here, the pressure integral evaluated over faces A and D yields the net sum, okay, the net sum of the pressure times the area at point A and pressure times the area at point 2, okay? So once again, the equal and opposite pressure forces on B and E will cancel out as do those on C and F. Hence, equation becomes this expression, right? So we equate it in this expression. Since A1 equal to A2, the same area, so we can now express it as the this expression, the pressure plus the density times the velocity at 1 and at 2 respectively. So let us now apply the integral form of the energy equation. So you have already done for the continuity equation, momentum equation, and then now we consider the energy equation. It's a similar condition, steady flow, F equal to 0, inviscid flow, and as well as adiabatic. So the energy expression is there. Again, noting that the flow is tangent to faces B, C, F, and E. Hence, the change of velocity with respect to the entropy will be equal to 0 on these faces. And the equation of energy will become as this, right? Okay. So let us continue, right? Where we now collecting term in the energy equation, we have this expression, right? So we rearrange that in terms of the enthalpy H, okay? So from here we can change into H1 and H2, divide by the continuity equation that we already obtained earlier. Then we have this. So we have the enthalpy expression, knowing that the V squared equal to U squared plus W squared, and W1 which is equal to W2, the equation then become as this expression of the enthalpy at station 1 plus the velocity squared over 2 at station 1 equal to the respective values at station number 2 downstream of the oblique shock wave. So now let's gather all the equations, right, from the continuity, momentum, as well as energy equation, right, for an oblique shock wave, right? So note that they involve the normal components only of velocity u1. So you know that now we can see that, oh, the expression are a component of velocity u1 and u2. The tangential component w does not appear in this equation, right? So hence, we deduce that changes across an oblique shock wave are governed only by the component of velocity normal to the wave. Again, if you look hard at the equation, look back at the equations, they are precisely the governing equations for the previous normal shock wave. So you can see that it is the same governing equations. All right. Hence, precisely the same algebra as applied to the normal shock equations in our previous lecture in topic number 2, right? Which lead to identical expressions for changes across an oblique shock in terms of the normal component of the upstream Mach number, which is Mn1. And note that where from the geometry, Mn1 equal to M1 sine beta, right? M2 equal to Mn2 over sine beta minus theta. All right, so from here, so hence for an oblique shock wave with Mn1 and Mn2, so this is Mn1 and Mn2 over here, okay, given by the above relations, to calculate the properties of the oblique shock wave as follows. All right, so hence for an oblique shock wave with Mn1 and Mn2, given by the relations that we have already seen before, to calculate the properties of the oblique shock wave as follows. So if you have normal shock wave, right, so you have M2 squared, this is what we have already expressed before, right? For the density ratio, the pressure ratio, and the Mach number squared at station 2. For the oblique shock wave, similarly, we will then re-express it as Mn squared at station 2. So you can see the comparison between the expression, right? Similarly, for the density ratio and the pressure ratio. So where we know already earlier Mn1 equal to M1 sine beta, and T, the temperature ratio, can also be expressed as the pressure and the density ratio. All right. So note that the Mn2 is the normal Mach number behind the shock wave. Okay, Mn1 is the normal Mach number before the shock wave. Okay, the downstream Mach number itself, M2, can be found from Mn2 using this relation. So we can find the downstream Mach number M2 from the value that we calculate for Mn2, and knowing the beta and theta through the derived equations. So it states that the oblique shock wave properties in a calorically perfect gas depend only on the normal component of the upstream Mach number, Mn1. However, Mn1 depends on both M1 and beta. All right. So we recall back, for normal shock wave depend on one parameter only, which is upstream Mach number M1. right? So you can look at our previous notes on topic number 2 for normal shock wave, okay, which is depend on the upstream Mach number M1, okay, but for oblique shock wave, it depends on both M1 and beta because it depends on the angle that of the Mach wave. Okay. However, so this distinction is slightly moot because a normal shock wave is a special case of oblique shock wave where beta equals to pi over 2, right? So basically that is 90 degree, beta is 90 degree. So knowing that tangent beta, which is U1 over W1 and tangent beta minus theta is U2 over W2, dividing these two equations and recalling that W1 is equal to W2 and invoking the continuity equation, right? So we obtain this expression of tangent beta minus theta over tangent beta, which is actually the velocity ratio and the density ratio. And combining this equation with our earlier expression of mn2 mn1 squared, so with the density ratio as well as mn1 equal to m1 sine beta, we then obtain this particular expression. All right. Now, derive this equation gives theta, right? So because earlier we know already what is beta, now we want to know what is theta as an implicit function of the m1 and beta. Okay. After some trigonometric substitutions and rearrangement, which we are not going to do it here, but I'm just going to show you the final result by having substitution as well as rearrangement. So this equation can be cast explicitly for theta, where you can find tangent theta which is equal to this particular expression. Take note that this equation is an important equation. It is called the theta beta Mach number relation, and it specifies theta as a unique function of m1 and beta. And this relation is vital to the analysis of oblique shock waves, and results from it are plotted in the next figure, which is a graph for gamma equal to 1.4, which is for the air properties. All right, so it is a little bit too small to see, but I really encourage you to look at the textbook for Anderson. You can actually zoom in terms of to see what is the relation. I put it side by side because in the textbook it is not on the same figure. So basically it is a continuous figure, right? So this is a graph of theta beta Mach number relation, right? So where you want to find what is the value of theta, okay, with respect to beta as well as the Mach number. All right. So we are going to use this graph from time to time, right? And we are going to find the respective value of theta, beta, or the Mach number. All right. So what we can see here from the graph of theta, beta, and Mach number relation, several physical phenomena can be illustrated for any given upstream Mach number M1. So if you look at the figure just now, there is a maximum deflection of theta. You can have maximum deflection of theta max. So if the physical geometry is such that theta is greater than theta max, then no solution exists for a straight oblique shock wave. So instead, nature establishes a curved shock wave, which detach from the corner of the nose of the body, which is illustrated in this figure below. So you can see here, if it is a wedge case, right? You can see that when a flow which is greater than Mach 1, right? You can see there's a attached shock where theta itself, right, is less than theta max. But when the Mach number, in another case where theta, which is greater than theta max, you will be seeing a detached shock, right? So it's generally the formation of the shock basically depend on the angle of the theta, whether it is greater or less than the theta max. Similarly over here, for the corner flow, again, Mach number more than 1, you can see that if it is less than theta max, it is an attack shock. You can smoothly see the attack shock formation. However, if it is more than theta max, theta equal to more than theta max, you can see that the shock already detached, right? So you are referring to the graph, and note that the value of theta max increases with increasing of the Mach number. So at a higher Mach number, the straight oblique shock solution can exist at higher deflection angles. However, there is a limit as Mach number approaches infinity, which is theta max approaches 45.5 degrees for gamma equal to 1.4. Right? So any given theta less than theta max, there are two straight oblique shock, which is oblique shock solutions for a given upstream Mach number. For example, if Mach number equal to 2 and angle equal to 15 degrees, so you can see from the graph, beta can equal either 45.3 or 79.8 degrees. So you may want to look at the graph just now. So you can refer where is actually what happened when Mach, the curve of Mach 1, sorry, Mach equal to 2 and theta equal to 15 degrees. And you can find the corresponding value of the beta, which is equal either 45.3 or 79.8 degrees. So the smaller value of beta is called the weak shock solution, right? And the larger value of beta is the strong shock solution. So you can, it's being represented in this particular sketch. And these two cases are illustrated in this particular figure. So the larger the wave angle, the larger the normal component of upstream Mach number m and 1, and then the larger the pressure ratio, P2 over P1. Thus, as in the figure, the higher angle shock wave will compress the gas more than the lower angle shock wave, and the terms strong and the weak solution is being used. In nature, the weak shock solution usually prevails. For the vast majority of cases involving the weak shock solution, the downstream Mach number is supersonic, which is more Mach 2, so M2 is more than 1. And since the weak shock solution is almost always the case encountered in nature, so we can readily state that the Mach number downstream of a straight attached oblique shock is almost always supersonic. All right. So before we stop our short break, let me just finish this. So if theta equal to 0, then beta equals either 90 degree or same as the Mach angle mu. Right? The case of beta equal to 90 degree corresponds to the normal shock wave. And the normal shock discussed in previous chapter belong to the family of strong shock solutions. So the case of beta equal to mu, right, the correspond correspond to the Mach wave illustrated in figure below. In both cases, the flow streamlines experience no deflection across the wave. So normal shock wave, what we seen just before, where actually beta equal to 90 degree. Okay, for Mach wave, where beta equal to 0 degrees. So this is the Mach wave. It is a flow at the tangent of line B to C over here. Okay, so consider an experiment where we have a supersonic flow over a wedge of given semi-angle theta, as sketched in the figure below. Okay, take 20 degree, we take theta equal to 20 degree, and Mach number equal to 2 as shown on the left figure. So from theta beta m, our Mach number graph, we find that beta is 53.3. So this value of beta is read from the graph, right? So you use the value of Mach number, use the value of theta, and you read the corresponding beta value from the graph, okay, which is 53.3 degrees. So now assume Mach number is increased to 5. So from 2, we then increase it to 5. So keeping the theta constant, you want to keep the theta is equal to 20 degree as sketched on this particular figure. Here we find that beta is now 29.9 degree. So in general, okay, from that two example over here, for attached shock with a fixed deflection angle, as the upstream Mach number increases, the wave angle beta decreases, right? So Mach number increases, the wave angle beta decreases, and the shock wave become stronger, going in the other direction as Mach number 1 decreases, M1 decreases, the wave angle increases, and the shock become weaker. So if M1 decrease enough, the shock wave will become detached. And for the case of theta equal to 20 degree, shown in the figure 912, 912 is the figure in the Anderson book, and the shock will be detached for Mach number less than 1.84. All right. So basically, before we go to the example, right, after the short break, I want to just to complete this. Consider another experiment, right? I hope you can bear with me for a couple more minutes. Here, let us keep M1 fixed. M1 is equal. M1 is equal to 2, and increase the deflection angle. You want to increase the deflection angle from 10 degree to 20 degree, right? So as shown here, take M1 equal to 2, Mach number 1 equal to 2, and theta equal to 10 degree. So the wave angle is 39.2, right, from the graph. So now assume the wave is such that we can increase its deflection angle, keeping the same Mach number, right? The wave angle increase as shown in the right figure. So you can see here, when you increase theta equal to 20 degree from 10 to 20 degree, you get beta equal to 53 degrees. So in general, for attached shock with a fixed upstream Mach number, as deflection angle increases, the wave angle beta increases and the shock become stronger. However, once theta exceeds the theta max, the shock wave will become detached. For the case of Mach number equal to 2, this is occur when theta is greater than 23 degrees. So with that, we want to take a short break.